So today we'll be studying linear maps, and we will show how we can convert all problems involving linear maps into matrix manipulations, and this will connect up nicely with what you are learning in your maths course. But before that, let's do a recap of crucial ideas from last lecture. And so let's look at some ideas that we had. So we had defined what we meant by a vector space over some field f, and for us f could be either reals or complex numbers. And we also saw the idea of a basis that was just a bunch of linearly independent vectors, the span of whom would give you the full vector space, and the dimension of the vector space is the number of these vectors. So if your dimension is n, you have n such vectors, and so we just call them e1, e2, so on and so forth up to en, and that we call it a basis. And so if you give me any vector, you can expand it in this basis, and you write it as summation from I equal to 1 to n ei ui, and we think of ui's as the component of the vector u. And it's useful to always remember that we write the basis vectors as a row vector. And if you want to do that, multiplication of matrices, you can multiply a row vector b in this case with the u. So you could write the same combination as a multiplication of a row vector multiplying a column vector. Okay, so the basis data is here, and this is the data of the vector. And this way of thinking about it, it just says that if you pick a basis, you can associate a column vector to every vector u. So, and once you see this, what are the elements here? Each of them will belong to f, so it will belong to f power n. So this is what makes all vector spaces of dimension n over a field f look exactly like either r power n or c power n, depending on whether we have real or complex vectors spaces. Okay, so another thing which we wanted to work out is that suppose we have two different bases. Obviously the entries that you would get in one basis b and a prime basis would be different. So you could write something else like this. So you would have the same vector, of course, but its components would be different because the basis is changing. So you could have b prime and a column vector with primes. That's what we call this vector. So one thing we saw was that these two bases should be related by some invertible matrix. Invertible is important, and so we could write this as ei equal to summation j equal to 1 to n ei prime sji, and so sji are the elements of this matrix S. And now I'm highlighting something in red here just to show you a little bit, remind you about how you multiply matrices. So when you have two matrices A and B that you're multiplying, the first matrix, the column index is summed over the row index of the second thing. So here we have this is just a row vector, so it has only column indices. So j is a column index, and this j of s is a row index. So we should always, when we have matrix multiplication, there's always a summation of this variety involved. Okay, so that's why this way of writing, you observe that we have to put the matrix S on the right of this thing. So we define this is kind of a compact notation, b equal to b prime s and b prime equal to b s inverse. It also tells you that you can go back and forth. S and s inverse should both exist, and that's what is the invertibility condition. And then you can just go back and you can show that u prime will be s times this column vector. Okay, and in sort of overuse of this notation of a dot, we'll use a dot to indicate matrix multiplication. Okay, so now let's move on to what a linear map is and how to obtain their matrices. Okay, so first thing is we just give a definition. So let V and W be two vector spaces over the same field F of dimension n and m respectively. So they don't even have to be the same dimension. A map T from V to W is a linear map if the following holds. Okay, it says so u and v are supposed to be two vectors in in the space V, and we are looking at its map. So T and A and B are scalars here. So T of AU plus BV is equal to A T of U plus B T of V. What does this say? On the left hand side, you first do the addition of vectors in the space V and then apply this map T and get an element of W. On the left hand side, what is it we are doing? We are first acting T on these vectors U and V, so that's T of U and T of B, and so now these are vectors in W, and this addition is being carried now in space W. Okay, so this is just a property which we want, and so this is, if this property holds, then we just call T a linear map. It's very, very simple. It's compatible with the linearity. Addition of vectors in V is compatible with the addition of vectors in W. Order doesn't matter. That's what it means. Now, here's an example. So we saw one example of one vector space, Pm of degree m polynomials in one variable x. Okay, so you can just go back, and so dy dx is just the standard derivative. So if you give me some polynomial like, x squared plus 2x, how does d by dx act on it? It acts on this thing. So x squared plus 2x, if you take a derivative, becomes 2x plus 1. Okay, so you have to show that that's a linear map with v equal to w equal to pm. So this is just an exercise, very, very simple, but to just show you, the reason to give this example is that this is kind of not something you think of as a linear map, but it is. Much more common examples of linear maps are the following. So let's do examples. So much simpler than the one which I just did. Let B be equal to W be R3. So this is like normal vectors. So U in this case is just U1, the column vector U1, U2, U3, but just to save space, I write it as U1, U2, U3 transpose. And the following two maps are linear. So T1 is the first map. It acts on U in the following way. It takes the column vector U1, U2, U3 and multiplies it with this matrix. What is this matrix? It's just like a standard rotation on a vector by an angle theta about the z-axis. So U3 prime is the same as U3, but U1 and U2 mix with each other. Scaling of a vector, T2 of U is AU, where A is some real number. So both of them you can easily check that they satisfy the basic condition, which is this. Okay, that's very easy to check. Now another example is with V equal to W, but this time it's C2, and you look at the theta polarizer. So theta polarizer was something which was doing something to the electric field, but from the viewpoint of this thing is just a linear map, and I didn't write out the matrix P of theta, but you can just go back and look at the previous lecture and then see what this P theta is. And so it's just a matrix, and so this is so it's again a linear map. Okay, so these are just examples, and in general we will show later, and this is kind of the important point of this lecture, is that if you give me a linear map, I can give you a matrix, and the condition will be that I will need to give a basis. Only then I can give you a matrix, but we'll see how that works later. But the real example, which is very, very generic and will map to this problem, is to consider the case when V equal to F power n and W equal to F power n. So these are simple ones, simple vector spaces. These are the first examples that we saw. And in this case, linear maps are m by n matrices. I'm just claiming that, but it's and the set of m by n matrices will be denoted by F mn. And this set can be made into an LBS, linear vector space, with the following two operations. But by the way, I mean, you can easily check that, just like we saw here, that if you take your vector and multiply it by a matrix, you get a linear map. So what I'm saying here is that any matrix, doesn't matter, it doesn't have to be a rotation, doesn't have to be scaling. It's just some arbitrary m by n matrix which can act on an n-dimensional vector, and output will be an m-dimensional vector, and that's a linear map. Again, that is something you can check, and it's a good idea to check. After some time you'll get bored, but it's something you can check. Now the key idea is that now you can look at all linear maps. In this case, they are just a set of all m by n matrices. This can be made into a linear vector space with just adding two operations. We know that operation. We need to have vector addition. So what's a vector in this space? It is just an m by n matrix. So you can just add two matrices, you get another matrix. So that's shows you addition. Scalar multiplication just corresponds to multiplying all the entries of the matrix by the same scalar. So if some t is some matrix, A times t is the new matrix. And so now let's look at this. The dimension of this vector space is mn. Why is that? Because if there is an arbitrary m by n matrix, it has mn entries and each one of them is independent of the other. Again, you can check this. And so the dimension is mn, but we can also be very explicit. So let A belong to numbers 1 to m, 1, 2, 3 to m, and B can take values from 1 to n, and oh, it should be I actually, not B. This is a typo. I should go from 1 to n. So let EAI, this is going to be a matrix, be a m by n matrix, which has only one non-zero element. So you go to the 8th row and the ith column and pick that guy entry and make that non-zero. If you want to be 1, you could put 1 there, but any non-zero number will do at the location AI in the matrix, and all the other elements are zeros. So we can do this in mn places, and these mn matrices provide a basis for fmn. So by explicitly constructing a mn dimensional basis, we can see that the dimension is mn. So now we will prove the same statement, but we did that for matrices. We would like to do that for linear maps. So we are no longer here. We did this for fn and the trivial cases, fn and fn. But now we will just write some arbitrary vector space v and w and construct all linear maps between them. Okay, so call this space T. The following two, I would call it obvious, but it may not be obvious. Operations convert it into an LVS. How does it go? So let's say T1 and T2 are two linear maps, and we need to define addition of them. So I'm just calling this in quotes, T1 plus T2. This is a map. This is a linear map which corresponds to addition. How should that work? So I have to tell you how it works on some vector in V. So it just says that you just take T1 of U plus and just add it. So this is just definition. So now we got addition. And what about multiplication? Again, we need to have scalar multiplication. So this is the map A dot T, which is corresponds to scalar multiplication. That's the obvious thing. Again, you do apply T of U and multiply it by the scalar. So you can see again that all the axioms of a vector space over the field F, of course, is satisfied. And again, in all these things, it's only closure which is important, and you will see closure happens. Okay. So now comes the interesting part. We would like to associate a matrix so that we can go back to working with matrices like we did in this example, these two examples, or more generally think of this. So how do we get a matrix? And so let's do that. And for that, we need to pick basis for both V and W. And we saw that what does that do? Once you pick a basis for V, it's n-dimensional, so it's really, we can identify it. I use the word isomorphic, but really what I mean by that is that for practical purposes, once you have a basis, it's as if we have an Fn. So let's just go back to the recap slide. So what you get in an arbitrary vector space is a basis plus this column vector. And so if your basis is obvious, we can equally well think of it as the object on the right hand side. But really the honest truth is that if you have an arbitrary vector space, you need to pick a basis to make this isomorphism or this identification work. Isomorphism is correct word, but we have not defined what we mean by that. So that's why I'm sorry I used it in an earlier lecture. Okay, so let's go ahead and do the following thing. So choose a basis. So B subscript V is E1 to En is a basis for V. BW F1 F2 up to Fn is a basis for W. So now I'll just define. So you're giving me a linear map. That means from V to W, let T be some linear map. And so we want to first work out what it does to the basis vector. So you just create this row vector, which is the image of E1, E2, En under the map T. So we just write T of E1, T of E2, so on and so forth. Okay. So so now let's look at this element T of U, and this is just notation. We just call this T of the basis V. But look at T of E1. What is this? it's E1 is a vector in V, and this map gives you, so this is, each one of these is a vector in W. So now we got a row vector of vectors in W. So now we can go ahead and write T of BV, which is the same as this. We can expand each of these in this thing. So if you look at in this thing, the first column of this will be the T of E1. The second one will be T of E2. I mean, of course, multiplied by F1, F2, BW is here. So in terms of matrix multiplication, you get for every T of E1 gives the first column, T of E2 gives the second column, similarly T of En gives the nth column. So we can combine all these things into this matrix, which we indicate by a boldface T. It's a M by N matrix. See, it's M rows because the M is the dimension of W and N is the dimension of V. So we get an M by N matrix. And so here I've just written out this statement that the jth row T of Ej, jth column would be just this element Taj. So A, as you go down the column, the row numbers change. So that's what you get. So we call T as the matrix of the linear operator, provided we are given these two bases, BV and BW. So this would be what we will call the matrix for this linear map. So this way we can get matrices for every linear map once we pick bases for the two vector spaces. Again, we need to ask, how do things change under basis change? So let us go back a little bit to the first recap. And if you remember, we saw that if you give, so there is an invertible matrix S for every change of matrix. So we start from B and go to B prime basis, and this S, or if you want to go from B prime to B, there's an S inverse here. So let's come back to change of basis. So let's say that BV equal to, so now there are two vector spaces, so we'll have S for the basis change in V and S tilde for basis change in W. So now the question is, how does this matrix change? This is a very important idea, and so the reason is that we don't want, in physics definitely, we do not want the answers that we get about something depend on the choice of basis. So we would like to, at the end of the day, ask, pick a basis, find a matrix. That's one thing we do. But we need to know which part of the matrix doesn't depend on the choice of basis, and that's really the goal for looking at this. So let us do this thing. So we recall this formula here, T of BV equal to BWT. That's our starting point. This is the definition of this matrix, boldface T. But now we go ahead and plug this in here. So BV is just this statement. And then the prime basis is BV prime dot S. This is again matrix multiplication. And similarly, BW is BW prime dot S tilde. So this equation is just putting in the change of basis. Now comes the next step, which is kind of obvious. I mean, the vectors, T only acts on vectors. S is a bunch of numbers, but B consists of vectors. So I would suggest you just sit down and explicitly write this out. You will see that this is the same as saying that T only acts on the basis vectors, and that's equal to BW prime S tilde dot T. So we have nothing happening on the right hand side. So this is what we have. So now this is telling you what this same map, this first line told you what the map T did in the basis BV and BW. But now we have an expression which tells you what T does on BV prime and writes the answer in terms of BV prime, BW prime. Okay, so that's what it does. But now the problem here is there is an S on this side. So what we do is multiply from S inverse on both the right side. So this S inverse will come here. So what we get is what we want. Finally, it says that T BV prime equal to B prime W S tilde dot T dot S inverse. So both the basis change in W and the basis change matrix in V come into play, and this is what we should have called T prime. So we write this whole thing that under a change of basis, the matrix for a linear map transforms as T prime goes to S tilde dot S inverse. Little bit more thinking we can do. Remember, T is a M by N matrix. So from the left, we can only multiply it by M cross N. N matrix can multiply it, while this S or S inverse both is N by N matrix. So you can see that there is no ambiguity when M is not equal to N. You know, you just It's very clear which has to come on which side, because matrix multiplication works only one way. You need the number of columns to equal the number of rows on the one on the right. So that condition will tell you this answer. So really there's no need to memorize this formula. Okay, except you need to memorize, only figure out where this inverse comes. Again, that is a convention. So now we are done with general linear maps, and we will look at two linear maps which are of interest in physics mostly. And since our focus is on quantum mechanics, we look two cases. The first one is when the vector space W is the field F itself. So one way of thinking of a field is a vector space of dimension 1. Okay, so that's I remember I told you to look up Hefferon or something for a definition of a field in the earlier lecture, but now I'm giving you a cheap definition. A vector space of dimension 1 is a field. Okay, so hopefully that's precise enough. Such linear maps are called functions. Why functions? What does a function do? You're given some space. In this case, our space is some vector space, and you give a vector, and the answer should be a number or a scalar. Okay, so that's why we call it a function. But it's a linear function. It's not an arbitrary function. So now, and we know it's an LBS. So linear vector space of linear function on V is called the dual space to V, and is denoted by V star. Okay, and its dimension is the same as dimension of V, which let's say is equal to 1. So the one set of linear maps that we will be interested in is linear functions, and the second one is when W equal to V. So that is linear maps from the vector space to itself, and such maps are called linear operators. Example of that is a theta polarizer. It's a linear operator from with V equal to C2. Rotation is also a linear operator. It took a vector in R3 to a vector in R3. Okay, and the dimension of this LBS is n times m, but m equal to n, so it's n square. And the matrix is now square, not rectangular like in general. It's n cross n matrix. But now there's only one vector space, so we can choose to use the same basis for BV and on both sides. So S tilde can be said to be 1. So T prime now will be S T S inverse. So now remember I've mentioned that we are always interested in things which don't depend on basis. So we can ask, are there objects of this matrix T or T prime such that which don't depend on the choice of basis? So here are two examples. One is determinant of T. So let's do that. So let's look at determinant of T prime. That's determinant of S, T, S inverse. Okay, so the determinant of product of three matrices is the product of the determinants of the individual matrices. But determinant of S and determinant of S inverse are inverses of each other, so they cancel. So we can see that determinant of T prime equal to determinant of T. What this says is that determinant is an important invariant. Similarly, trace is invariant. There's a cyclic property of a trace. Trace of ABC is equal to trace of BCA. So you can take this S to this side. SS inverse is 1. So trace of T prime will be equal to trace of T. But there's something much more deeper. If you give me a n by n matrix, the set of its eigenvalues are invariant. So it's actually the strongest statement that we can make, that the eigenvalues of this matrix are invariant. So special cases of that would be determinant and trace, and hopefully from maths you have learned how determinant and trace are determined in terms of the eigenvalues of the operator of the matrix T. Okay, so we'll now finish this half of this lecture with a summary and outlook. So the general idea is that if somebody gives you linear maps, see, the point is that a vector space may be defined in some very, very complicated fashion. I mean, who would have thought that, a bunch of polynomials is a vector space, but we have seen that that does satisfy a vector space. And d by dx, which is a derivative, is also a linear map. But the whole idea is that once you pick a basis, then linear maps become matrices, and now we are home, we can do standard matrix manipulations. And then we worked out how the matrix transforms under change of basis, and this is what you get. Now it's interesting that in your maths, I think they introduced you to something called the row reduced echelon form. So you're given some n by n matrix and you do some row manipulations, and then you get a particular different matrix. Let's call that matrix T prime, which is in a particular form, which is called the row reduced echelon form. And so you can go back, and this is an exercise for you to verify that row operations correspond to having S equal to identity, no basis change in V, but having a non-trivial S tilde, and actually S tilde I believe will be lower triangular matrices. So you can see that here's an example of using basis change to do something nice. So you have some random T given to you, and you bring T prime to a particular standard form, and then you can read off the rank. And now one more point here is that under these changes, rank doesn't change. So the rank of T is the same as rank of T prime. Okay. Interesting exercises. What does it have make sense for S tilde equal to 1, and then you do column manipulations? Is there something called a column reduced echelon form? That's for you to think about. V star, I mentioned, is a space of linear functions on V, and this is something which will appear in the next half of the lecture. We will see that there will be a notion of length introduced, and naturally we will get linear functions. And so this is something which we will see pretty soon. And linear operators, again, remember, are linear maps from an LVS to itself, and we saw under change of basis T prime goes to S, T, S inverse. Now in quantum mechanics, the matrix S is usually used to make T prime into standard form, and if the matrix is T is nice, it will be a diagonal matrix, and the diagonal entries would be the eigenvalues of that matrix. And in quantum mechanics, the linear operators will play a very, very important role. For instance, time evolution will be given in terms of some linear operator of some state of the system in quantum mechanics. So although we are doing what appears to be pure math, these things will have direct applications in quantum mechanics. And so I have some out of syllabus material, and I'll just flash it here, that you can get some subspaces from linear maps. One is called kernel of T, and other is called the image of T. I will be uploading this slides, so I will not be discussing this anymore, but you can play with this. This is a lot of fun stuff, and I will end here.